In this video I'm going to talk about the alternating series test, or it's also known as a Leibniz test. So let's say that we have a series, the series like this, and an infinite sum, and it's alternating, which means that like its terms with even index is greater than 0 and its terms with odd index is less than 0. Like it can be vice versa, but like it's enough to consider only one case, because like we can multiply the whole series by -1 and it reduces to the other case. So then we have the condition that it's monotonically, the absolute values of the terms are monotonically decreasing. So the next term, the absolute value of the next term is strictly, it's less or equal than the previous term. So it's not strictly decreasing, but just decreasing. And the third condition is that the terms tend to 0. So the limit of an is equal to 0. And then from these three conditions, we can conclude that the series converges. So let's prove this. So we are going to consider the partial sums. So let's say that Sn is a partial sum. So it's a1 plus a2 plus and so on plus an. So we denote this partial sum by Sn. So now we calculate the S2n S2n plus 2 and compare it to S2n. So we compare these two partial sums. So it's easy to see that so this partial sum is equal to S2n plus two terms. So plus a 2n plus 1 and plus a 2n plus 2, right? So this the terms with the even number, they are also they always greater than 0. So this is always greater than 0. This is always less than 0. And because the sequence is decreasing by absolute value, so this term by absolute value is greater than this term by absolute value, and it's negative. So we have basically added a greater negative term and then a smaller positive term, right? So this means that this would be this sum would be so like the sum of these two numbers in total would be so this in total would be less than 0, right? Because we added a larger by absolute value negative number and the smaller by absolute value positive number. So this would be less than S 2n. So we concluded that s 2n plus 2 is less than 2n. So here we can conclude that this is strictly less. No, it's not strictly less, it's less or equal, because they could be because we have the possibility of equality here, because the sequence is not strictly decreasing but just decreasing, so it's less or equal. Then we have here, so if these values are exactly the same by absolute value, then we added 0, so it's less or equal. Okay. So similarly, we conclude that the partial sums with not index, so Sn S2n plus 3 versus S2n plus 1. So this is equal this is plus a2n plus 2 plus a2n plus 3. So we see that this is greater than 0, this is less than 0, and again by absolute value the sequence is decreasing, so we added a larger or equal by absolute value positive number, and then a negative number which is smaller or equal by absolute value. So the sum of these two terms would be, so here was less than equal than 0, here it's greater or equal. Greater or equal than 0. Therefore, this whole sum is greater or equal than S2n plus 1, right? So let's now write the two inequalities together. So we have so because of this, we have the partial sums with even indices. They are decreasing, and because of this, the partial sums with odd indexes, they are decreasing, right? No, they're increasing. So okay, so so basically we write that S2 is greater or equal than S4, greater or equal than S6, greater or equal than S8, greater or equal than S10, and so on, S2n, and so on. So we have decreasing partial sums with even indices, and with odd indexes we have the opposite. We have S1 is less or equal than S3, less or equal than S5, less or equal than S7, and so on, less or equal than S2n plus 1, less or equal, and so on. So we have these two sequences of partial sequences of partial sums. So one of them is increasing, another one is decreasing, and we know that they're bounded because like, so let's write that so S2n so S2n is equal to S to n minus 1 plus a to n. So a to n, so a to n a to n is positive, right? So a to n is positive, therefore this is strictly greater than S to n minus 1, and S to n minus 1, so we know that the odd partial sums, they are decreasing, therefore this is greater or equal than S1. From the second inequalities, this one. Yeah, I said that they're decreasing, they're increasing. So the odd sums, they're increasing. So S1, which is equal to A1, which is a constant. So basically we concluded that the partial sums with even indexes, they're bounded from below, and here we see that they're decreasing. So they're decreasing and they're bounded from below, therefore like they converge. It's a well-known theorem that if a sequence is monotone and decreasing, and is bounded from below, then it converges. So we conclude that S to n converges. Similarly, we consider the odd partial sum, so s2n plus 1 is equal to s2n plus a 2n plus 1. So this term is negative because all the odd terms in the sequence are negative. Therefore, this is less than s2n, which in turn is less or equal than s2, which is a1 plus a2, which is a constant. So again, we see that the odd partial sums, they are bounded from above, and they increase. So it's an increasing sequence that is bounded from above, therefore it converges. It also converges. So now we see that both sequences like s2n and sn plus 1, so this sequence and this sequence, both of them converge, and we see that the difference between them, so s2n plus 1 minus s2n is equal to a2n plus 1. This is tends to 0 by the condition of the theorem. Here the third condition here. Limit of n is equal to 0, therefore the limit of both of these sequences must be the same. So the limit of s to n when n goes to infinity is the same as the limit of s to n plus 1 is the same. Let's denote it by L. And therefore the whole sequence of partial sums Sn also converges. And the limit is the same number L. Yeah, so this concludes the proof.